So today we'll be talking about a research on detection of widespread weak keys in network devices. So this was a research conducted back in 2012, but I feel it's still relevant these days on how weak keys can basically disrupt your cryptographic functions. So why does randomness matters in cryptography? So many public key cryptography like DSA, RSA, or elliptic curve, they all depend on a strong unique randomness. So this randomness is basically picking up a random number in a huge pool of numbers. So a private key is basically a number, a huge number, and it's only secure because you're picking one of them in a very random manner, right? So if at all, say your random number generation seems unique but is actually uh, you know a pattern based on randomness, then it can be really insecure in whatever your private key is trying to secure, either your websites or your Bitcoin or whatever. So a little bit background, this research basically covers two specific network protocols, that's transport layer security and secure socket shell. So TLS is used to basically establish secure communication between your servers and your client, and SSH is basically used to let you communicate to any other system on the same or different network in a remote manner. And the security in these protocols is established through the cryptographic algorithms like RSA and DSAs. So let us understand how RSA works. For the sake of this presentation, we'll stick to RSA and not DSA. DSA is a bit outdated. Actually, even in the latest TLS 1.3, they've also considered RSA a bit insecure and moved to elliptic curve cryptography. But for now, we'll be talking just about RSA. So it's the public key of RSA is made of two factors. One is N and one is E. N is made of two huge prime numbers, P and Q, and they are supposed to be kept as a secret and picked up really randomly. And in case they are not random, is where the problem arises, and that's what the research gets deep into. And E is an exponent which is used to encrypt the data that is being transferred between two parties. And the private key is basically e to the power minus 1 mod the product of p minus 1 and q minus 1, and in this equation the mod function is what creates the one-way hash and makes sure that you can't come back from d to p minus 1 or q minus 1. So, and in case someone gets hold of P and Q, it's pretty easy to land on E and then find out D. So, and so that's why it's really important to keep P and keys secure, even though N is public. So the problem is it's really hard to compute n separately because it's 1024-bit key, and brute forcing all the possibilities is computationally very impractical. But in case you factor out n into two parts, that's p and q, and find out another n which shares one of the prime number, say that's n1 and n2, and see p is common, which is multiplied by q1 and q2, and if someone gets hold of the shared prime p, that is where the problem arises. So, in this particular research, they've scanned 29 million TLS hosts, 23 million SSH hosts, and they've done it specifically on IPv4 addresses, not any of the IPv6 addresses. And they've used a specific command called nmap, which is called the network mapper, which lets you scan your network devices and all the protocols that it uses and everything, so that they can filter out all the devices using TLS and SSH specifically. And once they have the TLS certificates and the SSH host keys, they'll be able to figure out how many of these certificates which contain the public key share any of the prime numbers that we spoke about earlier. So now that they have the public keys, uh, they have a huge set, that is millions of public keys, and they have to find pairs amongst these public keys to find out that shared prime, right? So factoring out the common factor from n1 and n2 takes a really long time. So another way to do this is basically find the GCD, that's the greatest common divisor, and then figure out the common factor between n1 and n2. And also, before doing the GCD, they try to cut down the search space by figuring out the product tree and the reminder tree. The product tree is basically a binary tree where each node represents the uh, product of multiple RSA moduli, and the root node is basically the product of all the moduli. And then the reminder tree is used so that they can avoid direct pairwise GCD computation. So both of this process reduced their search space, and then they used Bernstein's approach to calculate the GCD, which instead of a logarithm algorithm used a constant time based algorithm, which reduced their search from almost 30 years. That is, in case they had to brute force between every pair of n1 and n2 with all the million public keys that they had, from 30 years to 1.3 hours. Yeah, so it basically costed them $5 of computation power on AWS per hour. So yeah. So the basic idea was to figure out the shared prime between the two public keys from the huge set of data that they had. So they created pairs and performed GCD on them to figure out if they both had a shared prime. Consider 77 and 49 as the two public keys, and performing GCD on them would give us 7, which basically means they do share a prime. And using Bernstein's approach, it was easy for them to calculate Q1 and Q2 from the common prime that they gotten. The findings were that 5.57% of the TLS host shared keys, and 9.60 of the SH host used duplicate keys. And from the millions of public keys that were fetched through their scans, this is a really huge number, right? So the most common causes were because most of the manufacturers did not really bother to change to change the default keys, in the network devices that they used, and it also involved using low entropy key generation process, which basically means less randomness, and also snake oil TLS certificates, that is the default certificates. Let's say the C authorities had provided a set of instructions saying install this, use a certificate, and gave an example certificate, and so on. So they went ahead and used those example certificates without really knowing the real use case of it. So most of the network devices that we spoke about, the vulnerable devices, they're all headless and embedded devices, and most of them either run on Linux-based systems or Windows systems, uh, which used a specific library called Debu Random. Debu Random is a very common cryptographic library, which is very common in most of the OSs. Um, their documentation specifically says, you know, as a general rule, Debu Random should be used for everything except long-lived keys, like that is used in TLS, SSH, GPG keys, and all those. Uh, so why do they specifically mention this? Is because uh, it takes the input entropy in different forms, say mouse movements or keyboard movements, the CPU clock time, and so on. But since these network devices did not really consume a mouse or a keyboard, they were basically headless. Uh, those randomness did not really get into the factor, and it was always a constant value. And also, when such devices are not connected to the internet, uh, the time on their the boot time or the disk timing is not fetched from the network. The clock on their system will always start from zero. So if it's generated right after the boot, no matter what the current time is, it always picks up uh, a specific value after the boot, right? So yeah, that's pretty fascinating. If you look at how these Linux-based systems or Debu Random and OpenSSL libraries use these private key generation methods, they all used in the first initial boot when the system started, and since every uh, change or entropy that required needed at least 192 bits before they changed the value of the private key or the prime numbers that they needed, and they did not have any keyboard or mouse or real-time devices, real-time clocks to add the entropy. Uh, they were all basically deterministics in the way they produced the private key. So if we take a look at this particular graph, uh, the blue line here shows the number of entropy bits that were added during the first few seconds, and the blue solid line is basically the minimum threshold that it needs to change the value of the entropy for that particular key. And if you notice, almost until 65 seconds, they did not have anything new to be added uh, because of no real time keys or headless devices. And if any of the keys were being generated anytime before that particular threshold, they did not have any kind of randomness, and they were all deterministic. Right, so that was the main cause of predictable randomness in the primes that were being generated for RSAs. So if you have a look at the stats from few of the uh, embedded systems that generated these random numbers, some Linux-based systems like Jupyter SSG20, uh, they used a huge set of prime numbers, but also uh, they had, since they used default keys and shared primes, um, you see the red graph that is shown here are all related to the vulnerable random numbers which the authors were able to reproduce, and the ones on the black are that used actual randomness to produce the prime numbers and secure. And also surprisingly, one of the IBM machines, they in total used just 9 prime numbers to produce all of their random numbers. So if you take a look at this graph, there's a huge pile of uh, red blocks which represents the vulnerable uh, random numbers that were generated because it was easy to factor out shared primes from just 9 numbers that they actually used. So, as solutions and recommendations from the authors, they reached out to almost 40 companies and library manufacturers, etc., whoever used deterministic randomness, and mentioned that they had, vulnerability in the way in which they produce their randomness for cryptographic key generations. Uh, they also released patches on Linux kernels to improve the Debian random library. Uh, Also, with the network devices which had access to the internet, they added real time uh, data as a part of their randomness. And they also enhanced early entropy collection, whichever used it during the boot time. And as best practices, manufacturers must generate keys securely at factory. So, since we know that a lot of them use their default keys, as manufacturers, they had to be responsible enough to make sure that the randomness they generate are not deterministic. And libraries should default to high entropy sources, make sure they're meant specifically for key generation and not any cryptographic library. And administrators who distribute these devices, they need to make sure, in spite of uh, manufacturers using any kind of random keys, they need to replace them and make sure they have their own layer of security on top of it. And they should also make sure they are on top of all the new patches that come in and have regular audits and so on. Takeaways from the authors were that almost over 5% of the TLS and 9% of the SSH hosts used compromised keys, and particularly the embedded devices were vulnerable on such issues. And the random numbers generation remains, it's still a weakness because there are also researches going on how elliptic curve uh, can also have a backdoor in the way in which the people who recommends ACDSA, they do also recommend using a specific kind of prime, which is still not very clear on why they expect us to use a specific kind of prime. And there are ongoing researches and references in the paper that talk about how even ACDSA can be a problem. They also say that, and since the researchers, they also have established such large scale measurement It should be easy for anybody to basically collect such vulnerable devices and make sure things are fixed. And also, proper cryptographic hygiene is recommended, specifically in embedded devices, because they're all headless and they do not have any external source of input which is needed to add entropy in such devices. So, at future research directions, there are really great resources available online which talks about how, like we spoke, how ECDSA and such vulnerabilities uh, exist, because the people who recommend the library, if they do know the primes that are being generated, or at least the way in which the primes are being generated, um, even they could be vulnerable. And uh, maybe see how TCP/IP sequence numbers, etc., are all vulnerable in the same manner, because they all use the same kind of key generation and uh, the same kind of entropy management. Thank you. That's been about it.